400 HE power systems find applications in aircraft and some shipboard environments due to the advantage of enabling the use of smaller and lighter transformers and motors. In the context of aircraft, the electrical distribution system usually involves a three-phase, four-wire configuration. A key aspect of this system is the bonding of the neutral conductor to the aircraft structure, specifically at the transformer location. This bonding is essential for providing a lower impedance path for fault currents. It also plays a role in preventing the accumulation of static charges on the aircraft, which is a safety consideration. In a 400 HE power system, the typical practice is to avoid grounding the neutral conductor at the distribution boxes. This is because the higher frequency inherent in 400 HE systems influences the behavior of current flow within conductors. The higher frequency reduces the skin effect. The skin effect is a phenomenon where alternating current tends to flow more along the surface of a conductor than through its core. By reducing the skin effect, the neutral conductor can carry more current without experiencing excessive heat buildup. Bonding the neutral conductor to ground at multiple distribution boxes introduces a potential issue. It creates a parallel path for fault currents. This parallel path can lead to an uneven distribution of current and potentially result in overheating of the neutral conductor, especially if it's not adequately sized for the combined fault current. While the National Electrical Code, or NEC, serves as a comprehensive standard for electrical installations, it's important to recognize that it does not provide specific guidance or regulations for 400 HE power systems. Given this lack of specific direction within the NEC, it becomes critical to consult with the equipment manufacturer. Manufacturers typically provide detailed grounding requirements and recommendations tailored to their specific 400 HE power system components. These recommendations are vital for ensuring the safe and reliable operation of the system. There have been instances where the neutral conductor in a 400 HE power system was intentionally bonded to ground at the distribution boxes. However, these cases typically involve a specific design consideration. In these situations, the neutral conductor is sized to accommodate the full load current. This oversizing is necessary because the bonding of the neutral conductor to ground creates a parallel path for fault currents, and if the conductor is not appropriately sized, it could overheat due to the increased current flow. A potential drawback of bonding the neutral conductor to ground at multiple distribution boxes is the creation of a ground loop. A ground loop occurs when there are multiple paths to ground, creating a loop where unwanted current can circulate. This circulating current can manifest as noise and interference within the electrical system, potentially affecting the performance of sensitive equipment. To mitigate the effects of ground loops, several strategies can be employed. Firstly, the use of shielded cables can help to reduce electromagnetic interference. Secondly, grounding the system at a single point helps to avoid creating multiple ground paths, minimizing the potential for circulating ground loop currents. In summary, while the NEC doesn't explicitly address 400 HE power systems, understanding the unique characteristics of these systems is crucial. The practice of bonding the neutral conductor to ground requires careful consideration of factors such as conductor sizing and the potential for ground loops. Consulting with equipment manufacturers and implementing appropriate mitigation strategies are essential for ensuring the safe and reliable operation of 400 HE power distribution systems. When working with electrical systems, adherence to safety guidelines is of utmost importance. Always energize circuits before working on them and use appropriate personal protective equipment. If you are not qualified to work on electrical systems, consult with a licensed electrician. The principles of grounding and bonding are fundamental to electrical safety. Grounding provides a path for fault currents to flow back to the source, tripping a circuit breaker or fuse and preventing electrical shock. Bonding ensures that all metal parts of an electrical system are at the same potential, reducing the risk of electrical shock. In a typical 60 HE system, the neutral conductor is grounded at the service entrance. This provides a reference point for the voltage and helps to stabilize the system. The equipment grounding conductor is connected to the metal parts of the electrical system and provides a path for fault currents to flow back to the source. In a 400 HE system, the grounding and bonding requirements may be different depending on the application. It is important to consult with the equipment manufacturer and follow their recommendations. The size of the grounding and bonding conductors is also important. The conductors must be sized to carry the maximum fault current that could occur in the system. The NEC provides tables that specify the minimum size of grounding and bonding conductors based on the size of the overcurrent protection device. Ground fault circuit interrupters, or GFCIs, are an important safety device that can help to prevent electrical shock. GFCIs monitor the current flowing in the circuit and trip the circuit if there is a ground fault. GFCIs are required in many areas, such as bathrooms, kitchens, and outdoor locations. Arc fault circuit interrupters, or SIs, are another important safety device that can help to prevent electrical fires. SIs monitor the current flowing in the circuit and trip the circuit if there is an arc fault. Arc faults can occur when there is a loose connection or damaged insulation. SIs are required in many areas, such as bedrooms and living rooms. Surge protective devices, or SPDs, can help to protect electrical equipment from damage caused by voltage surges. Voltage surges can be caused by lightning strikes, power outages, and other events. SPD divert the surge current to ground, protecting the equipment from damage. Regular maintenance is important for ensuring the safety and reliability of electrical systems. This includes inspecting the wiring, connections, and equipment for any signs of damage or wear. It is also important to test the GFCIs and FSIs regularly to ensure that they are working properly. When troubleshooting electrical problems, it is important to follow safe practices. Always to energize the circuit before working on it and use appropriate personal protective equipment. If you are not qualified to troubleshoot electrical problems, consult with a licensed electrician. Understanding electrical schematics is important for troubleshooting electrical problems. Electrical schematics show the wiring and connections of the electrical system. By understanding the schematic, you can trace the circuit and identify the problem. Electrical test equipment is essential for troubleshooting electrical problems. This includes a multimeter, a clamp meter, and a circuit tracer. A multimeter can be used to measure voltage, current, and resistance. A clamp meter can be used to measure current without disconnecting the circuit. A circuit tracer can be used to trace the circuit and identify the location of a break or short. Proper grounding and bonding techniques are crucial for maintaining electrical safety in both 60HE and 400HE systems. While the NEC provides comprehensive guidelines for 60HE systems, specific considerations apply to 400HE systems due to the higher frequency characteristics. In 400HE systems, the skin effect becomes more pronounced, influencing current distribution within conductors. This necessitates careful attention to conductor sizing and grounding practices to prevent overheating and ensure reliable operation. Consulting with equipment manufacturers is paramount, as they provide specific grounding recommendations tailored to their 400HE power system components. Additionally, mitigating ground loops is essential to minimize noise and interference within the system. Shielded cables and single-point grounding techniques are effective strategies for achieving this. Regular maintenance and inspections are crucial for maintaining the integrity and safety of electrical systems. This includes verifying the proper functioning of safety devices such as GFCIs and FSIs, as well as inspecting wiring and connections for any signs of damage or wear. When troubleshooting electrical problems, prioritizing safety is paramount. Always to energize circuits before commencing work and utilize appropriate personal protective equipment. If you lack the necessary qualifications, seek the assistance of a licensed electrician to ensure safe and effective troubleshooting. Adhering to these principles promotes electrical safety and ensures the reliable operation of electrical systems in both residential and industrial settings. Let's delve deeper into the nuances of grounding and bonding, particularly in the context of 400HE systems. Grounding, at its core, establishes a reference point for the electrical system, typically at 0 volts. This reference point is crucial for maintaining voltage stability and preventing the accumulation of static charges. In 60HE systems, the neutral conductor is typically grounded at the service entrance, providing a direct path for fault currents to return to the source. Bonding, on the other hand, ensures that all metallic components of the electrical system are electrically connected, creating an equipotential plane. This equipotential plane minimizes the potential difference between metallic objects, reducing the risk of electric shock. In 400HC systems, the grounding and bonding requirements may differ due to the higher frequency characteristics. The skin effect, as mentioned earlier, becomes more prominent, causing current to flow primarily along the surface of conductors. This necessitates careful consideration of conductor sizing and grounding techniques to prevent overheating and ensure efficient current distribution. One common practice in 400HC systems is to ground the neutral conductor at the transformer, providing a reference point for the voltage. However, grounding the neutral conductor at multiple points along the distribution system can create ground loops, which can introduce noise and interference. To mitigate ground loops, single-point grounding techniques are often employed. In single-point grounding, all grounding conductors are connected to a single grounding point, preventing the flow of circulating currents. Shielded cables are also used to minimize electromagnetic interference, further reducing the potential for noise and interference. In addition to grounding and bonding, surge protection is an important aspect of electrical safety. Voltage surges caused by lightning strikes, power outages, or other events can damage sensitive electronic equipment. Surge protective devices, or SPDs, are designed to protect equipment from voltage surges by diverting the surge current to ground. SPD are typically installed at the service entrance and at individual equipment locations. Regular maintenance and inspections are crucial for ensuring the continued safety and reliability of electrical systems. This includes inspecting wiring and connections for any signs of damage or wear, as well as testing safety devices such as GFCIs and FCIs. GFCIs, or ground fault circuit interrupters, are designed to protect against electric shock by detecting ground faults. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. GFCIs trip the circuit when a ground fault is detected, preventing electric shock. ASIs, or arc fault circuit interrupters, are designed to protect against electrical fires caused by arc faults. An arc fault occurs when there is an unintended electrical discharge between two conductors. ASIs trip the circuit when an arc fault is detected, preventing electrical fires. When troubleshooting electrical problems, it is essential to follow safe practices. Always to energize the circuit before working on it, and use appropriate personal protective equipment. If you are not qualified to troubleshoot electrical problems, consult with a licensed electrician. Understanding electrical schematics is crucial for troubleshooting electrical problems effectively. Electrical schematics provide a visual representation of the electrical system, showing the wiring and connections of the various components. By understanding the schematic, you can trace the circuit and identify the location of the problem. Electrical test equipment is essential for troubleshooting electrical problems. This includes a multimeter, a clamp meter, and a circuit tracer. A multimeter can be used to measure voltage, current, and resistance. A clamp meter can be used to measure current without disconnecting the circuit. A circuit tracer can be used to trace the circuit and identify the location of a break or short. In conclusion, proper grounding and bonding techniques, along with surge protection and regular maintenance, are crucial for maintaining electrical safety in both 60HC and 400HC systems. Adhering to safe practices and seeking the assistance of qualified professionals when needed are essential for ensuring the safe and reliable operation of electrical systems.